Hey, welcome back to Math with Patrick. Today is May 28th, and we're solving problem number 148 from the Daily Epsilon calendar. And we need to show that x is equal to 28 today. So it looks like we're given two different equations, and we have two different unknowns. So maybe we can learn a little bit something about r and s from these two equations. And then once we figure out what r and s are, we can then evaluate for x. Although at first glance, this does seem a little tricky. Usually, it's kind of hard to connect linear equations with exponential ones. And so let's play around with the numbers and just kind of see what happens real quick. So if I make a table, R, S, both of these need to add to 2. So maybe 1 and 1 could work, maybe 2 and 0, maybe 0 and 2. And let's just kind of see what happens when I try that second equation. 2 to the r plus 2 to the s. So here it'll just be 2 plus 2, which is 4. Oh, here it's also going to be 4 plus 0. 4 plus 1. So this will be 5. And since everything is just kind of symmetrical here, this is also going to be a 5. I think I'll probably need one of r or s to be negative here because, I don't really think I'm going to be able to do like a 1.5 and a 0.5. I think that's going to land somewhere between 4 and 5. I'm not entirely sure, but it looks like I'm not going to get some nice, easy whole number solutions for r and s. If I tried negative numbers, right, I could say r is 3, s is negative 1. But then I get 8, right, because 2 cubed is 8, and then plus a 1/2. And so now I'm overshooting that 6. So maybe r is 2 point something, and then s is whatever the necessary decimal to bring it back to 2. I don't think I'll actually be able to directly solve for s. Instead, how about let's try to play around with the algebra here and see if we can produce a 4 to the power of r out of this. Let's see, so what can we do? Let's try substitution. I'm going to isolate r and s from this one and then plug in the right ones into the other equation to try to see if I can find an expression for these or something. I'll just try it out. So to isolate r, all I have to do is subtract s to the other side. And everything is really symmetrical here. So I might just actually do both at once just to kind of match it up. So s will also be the same thing. S is just 2 minus r. Here, all I'm doing is subtracting this r to that side. That lets me do some substitution. So if r is equal to 2 minus s, I could do 2 to the power of 2 minus s, because that's the same as r. And I'll leave the rest of this equation the same. Over here, I will substitute out the s, and so I'll get something that looks like this. And then how about, let's do some factoring. My overall goal was to maybe find a 4 to the power of r or 4 to the power of s. And I think if I factor out a 2 to the power of, how about negative s? I think I'm going to get what I want. So whenever you factor stuff out, you can think about this times another thing is going to bring you back to where you started. And when we're multiplying things with the same base, so I know that the base should be 2, all we got to do is add the exponents. Negative s plus that will bring me back to my original exponent here. So that means this should be 2 to the power of 2. And this should be 2 to the power of, I guess, 2s, right? Because if I add these exponents together, then I will remain with just 1s in the end. That's all equal to 6. And I'll kind of copy down my idea here. I'll just say 2 to the power of negative r and basically rewrite exactly what I have, but I'll make sure it says 2 to the power of 2r on this one. Okay. And then I do get a 4 to the power of s here. There is an exponent rule that you could use where if you have some kind of base to the power of multiplied exponents, you are totally allowed to evaluate the exponents 1 at a time. And in this case, I'll do 2 to the power of 2 and then the power of s, and then here's where that 4 is that I wanted. So I'll rewrite everything in a more simplified format. I think I'm still stuck with this 2 to the power of negative s, but I at least can write the inside part as 4 plus 4 to the power of s. That's still all equal to 6. So this will still be 2 to the negative r, and then 4 plus 4 to the power of r equals 6. And then hopefully I can like isolate this and this, because those are some expressions that I see here that are going to be useful to solve for x. So to isolate 4 to the power of s, I want to multiply this to the other side to make sure I keep it balanced. What should I do? I'll do 2 to the power of s, I think, because like, x to the fourth times x to the negative fourth, these two things cancel each other out and create the number 1. And so if I multiply 2 to the s there, I should multiply 2 to the s. Oops, that's s squared. I should multiply 2 to the s here to keep my equation balanced. I'll do the same steps over on the right. It'll be 2 to the r on one side and 2 to the r on the other. All right, that tells me that 4 plus 4 to the s is 6 times 2 to the s, and 4 plus 4 to the r is equal to 6 times 2 to the r. I wanted to isolate these guys, so how about let's subtract 4 from both of these equations and see what happens. 4 to the s is equal to 6 times 2 to the s, minus 4. And then 4 to the r is equal to 6 times 2 to the r, minus 4. And supposedly when I add this and that, I should get x. So let me kind of write out that last equation from the prompt just to kind of like keep all my thoughts in check. So it does say 4 to the r plus 4 to the s is equal to x. So I'll do some substitution. I could sub in my 4 to the r expression from on the right. So I'll get something like that. And then I'll add 6 times 2 to the s minus 4. That's still supposed to be all equal to x. And how about we should combine our minus 4s together? That'll just be a minus 8. And then how about let's factor out this 6. 6 times, and then 2 to the r plus 2 to the s. So if you like distribute out the 6 again, we're going to get this term and this term, and then this minus 8 covers both of these minus 4s. And what's kind of cool here is actually I returned back to my first equation, 2 to the r plus 2 to the s, or I guess the second equation. That's this one right here. This is the number 6. So I could substitute out that whole expression. I don't even know what r or s is, but I do know I can do 6 times 6 minus 8, and I will get x for today. 6 times 6 is 36, and then 36 minus 8 does give me 28. Wonderful. Cool. So x is 28. That's today's date. And I have no clue what r and s are. How about just to like kind of solve the whole problem, maybe I can find r and s graphically. So let's hop on over to Desmos. So instead of r and s, I'm going to pick x and y just so Desmos can like show me something. So 2 to the x plus 2 to the y is equal to 6. And then the sum of x and y should be 2. And so, I actually get, that makes sense. I got 2 solutions here. And to me, it makes sense because like everything was super symmetrical about r and s. So it could have been either way. Maybe r was the one that was negative or r was the one that was positive and vice versa. And so just because I'm going to pretend that r was positive, I will look at the solution where x is positive. So it's this one right here. And I can't really tell what value this is, honestly. Looks like it's around like 2.4 and negative 0.4. Although, oops, that should have been a comma first. Though that doesn't really match the red curve perfectly. And I don't really know what this value is, to be honest. I can't really quite place it. And here I'm just kind of like guessing and checking until I get kind of close. And this number doesn't look too familiar to me. Like, I know that root 2 ends in like this kind of decimal with like the 0.41. So I was predicting maybe 2 root 2 could have been an answer because it is between 2 and 3, but it's not really landing where I want. Maybe the exact answers have like logarithms in it. And so the last place that I'm going to check is actually Wolfram Alpha, because maybe that can solve the system of equations more accurately for me. All right, let's see how this fares compared to Desmos. I'll put in x plus y equals 2, and then 2 to the x plus 2 to the y equals 6. Run it, see what happens. There's the same graph that we saw. And then, I mean, it's just kind of giving me the real solutions as decimal approximations. Oh, I could click exact forms. Whoa, okay. So I guess it kind of makes sense that the exact solutions are going to use logarithms because we were dealing with like exponential equations, and the opposite of exponents is logs. And I guess these are our exact solutions. I'm not quite sure how I'd get it myself, to be honest, but it's kind of cool that, I could use the technology and figure it out. So this value is going to be the negative version. And then if I add 2 to it, or I just click on the other one, this one right here, this one is going to be our other solution for today. Or, well, not the solution, but the values for R and S. All right, guess we're all done. I don't think there's much more to explore. Maybe you could figure out on your own how you could create this kind of exact answer instead of relying on decimals or graphing or whatever. Actually, lastly, I just want to show why those values work. So let me work over here in the corner. The exact answers we had, I'll just say R is equal to, and then it was, let's see, what Wolfram Alpha said was log 2 on the bottom, and then log 3 plus or minus root 5 on the top. And what I can do here is use the change of base rule and rewrite this value as log base 2 of 3 plus or minus root 5. And we can plug in this number into the first equation and kind of see what happens. That was just R plus S. So it'll be log base 2 of, say, the positive one first, and then add log base 2 of the negative one second. And this should evaluate to the number 2, because that's what it was up above. I can use a log rule where if I have the sum of logarithms, I can change it to the log of a product. And so I can multiply these arguments with each other on the inside here. And since I have something kind of like a difference of squares factoring on the inside, I know I can evaluate this as log base 2 of 9 minus 5, which is log base 2 of 4, which is 2. And that's satisfying the first equation. And then secondly, if I try figuring out what happens when I plug into the second equation, all I really need to do is raise both of these values, or raise 2 to the power of both of these values, and then add it together like that, and I should get the number 6. Logs and exponents are opposites, so I can basically just cross off these, and I'll get 3 plus root 5 plus 3 minus root 5. And then those root 5s cancel, and I'm just left with 6. So there's something kind of interesting going on with the difference of squares factoring in there, with some log rules, and ultimately I can verify that these exact answers do fit. But I think it would still be a really hard challenge to be able to see these first two equations and produce those values on your own. So I just wanted to show a little bit of algebra at the end to verify those exact answers, and now I'm all done. The answer is 28. Let's get on out of here. All right, bye.